Okay. Okay, so let's move on to the next presentation. So the next presentation is accelerating RISC-V hardware and software development using fast processor models. The speaker is Mr. Lapides, Synopsys, formerly Imperas, because Imperas just acquired by Synopsys several weeks ago, maybe, right? So 次のご講演は高速プロセッサーモデルを使用して RISC-V ハードウェアおよびソフトウェア開発を加速です。講演者はシノプシス、少し前までインペラスでしたのラピデス様です。So would you start?
Thank you very much. Very excited to be here in Japan again. Very excited to present here at the RISC-V Tokyo Days. As was just mentioned, Imperas has recently been acquired 1 month ago by Synopsys. So the Imperas team is now inside of Synopsys. But I will be talking about the Imperas technology here today. But first, let's talk about RISC-V. And I think one thing that that sometimes gets lost here, it is the freedom of RISC-V and not the free. That is why RISC-V is growing so fast. RISC-V is a modular technology so that you can put in the extensions that you want. It also allows for custom instructions, and it is this freedom that is the key. So I'm going to start today by talking about why RISC-V, why processor models are so important, and why Synopsys and Imperas are so important for this. And then talk about some of the details of the processor models, and then the 3 use cases: architecture exploration, processor verification, and software development, and then wrap up. So let's get started here. So RISC-V processor world. RISC-V is an open standard instruction set architecture. It is not open source. The RISC-V freedom is what enables these domain-specific processors. And again, it's this freedom and not the free that is driving and accelerating RISC-V adoption. Here you go. So what are the sources of RISC-V processor implementations? There are 3 different ways that people build RISC-V processors. One is that they license the processor IP from one of the RISC-V vendors. We've had a few of those this morning already. A second is open source implementations. There are open source implementations as well. And the third is to build the RISC-V processor from scratch. With all these implementations, custom instructions and custom configurations will be used. And with all these implementations, even with well-verified processor IP that you license, the processor plus the custom features must be designed and verified. And also, do not forget about the software costs that are associated with RISC-V, the toolchain, the software porting. RISC-V is not free, but it is that freedom for a domain-specific processor that is the key to RISC-V. Why are processor models so important to RISC-V's success? The key tasks that we have seen, so Imperas has been involved in the RISC-V community now since the very beginning. So this is over 7 years we have been involved. The key tasks for RISC-V processor development and use are architecture exploration, especially adding custom instructions and CSRs, design verification, and software development. Architecture exploration is most efficiently done with a high-level model. You do not want to use RTL for experimenting with architecture. It just takes too long. Design verification of a processor requires a reference model. So again, the need for a model. And software development, especially for complex processors and for SoCs in markets with reliability, safety, and security requirements, are most efficiently developed. The software is most efficiently developed and tested with software simulation or virtual prototypes, which require models. And this model needs to be more than just an instruction set simulator. On the Imperas side, as I mentioned, we've been working with RISC-V for quite a while. It is 7 years now that we've been working with RISC-V. Actually, we started in 2007, Imperas did, building models of ARM and MIPS and Renaissance and other architectures. RISC-V is just for the last 7 years for us. Our first paying customer was in 2018, using Imperas RISC-V models and tools for both software development and for processor verification. And then the first tape out of a RISC-V SoC based on using the Imperas model as the design verification reference model was in 2019. Important in Japan, I think, was we started working with NSI Techs on RISC-V projects, including the government projects Trazio and RBSPF in 2019. We have continued to add products to our portfolio to expand beyond just the models. And right now, most serious RISC-V processor projects are using Imperas technology. So let's talk about those RISC-V models. So high-quality RISC-V models are required for RISC-V success. Again, for those three use cases: architecture exploration, software development, processor and SoC verification. Anyone can build an instruction set simulator. Everyone has built an instruction set simulator. Probably most of us in college built something along the lines of an instruction set simulator. But actually more than just an ISS is needed. So what are some of these requirements? So yes, just like an instruction set simulator, you need to model the ISA, the instruction set architecture, including all versions of the ratified spec and all stable unratified extensions. Need to be able to model the other behavioral components in the RISC-V world. You need to be able to easily update and configure the model for the next project, because you are not just doing one generation of RISC-V. It needs to be user extendable for custom instructions and registers. You need to be able to model the actual processor IP if you're working with a vendor. There needs to be a well-defined test process for the model itself, not just for the RTL, but the model is going to be used there. And so you need a well-defined test process, including coverage metrics and mutation testing, so that you understand the quality of your test bench. Needs to be able to interface to other simulators, including System C and System Verilog. Needs to be high performance for software simulation. Needs to interface to software debug tools. Needs to interface to software analysis tools. Needs to interface to architecture exploration tools. Most RISC-V instruction set simulators can meet one or two, maybe three of these requirements. But the Imperas models and simulators were built to satisfy these requirements and matured through usage on non-RISC-V instruction set architectures over the last 15 plus years. So let's move on and talk about the architecture of the model. So actually what we do at Imperas is build the model using a set of APIs. So the models are built in C and built with APIs, and the Imperas simulator actually supports those APIs and executes that functionality. So the base model implements the RISC-V spec in full. It is built using a test-driven development methodology to get the high quality that we need, and built using those APIs. Then we add in a configuration file because RISC-V is highly configurable. So this is user configurable to select which extensions and even which version of each extension. We now support, I don't know, 4 different versions of bit manipulation, maybe 6 different versions of the vector specification, because it has been stable and users have needed a model at that version of the extension. For the processor IP vendors, we have another configuration file that also adds in the custom instructions, which some of the processor IP vendors have. And then we have this user extension library for custom instructions and CSRs. So what this does, this means that custom instructions are in a separate file from the base model. So when you add whatever your custom instruction is, it does not change, it does not perturb the base model. All the Imperas RISC-V models, and we have models of over 100 different processors, RISC-V processors, they all use the same RISC-V base model. So actually, the RISC-V base model, again, it's used in all those RISC-V processor models. It's used by our commercial users. It's used by academic users. And we do have a free instruction set simulator, RISC-V OVP Sim Plus. So this RISC-V base model is used by more than 150 different organizations. So it is very thoroughly tested internally by Imperas, very thoroughly used by our customers. So we take that model, this base model with the configuration, with the user extensions, and because it is built using the same APIs, it looks like a single reference model to the tools. And then it gets used for processor DB. And we see here not just the reference model, but also functional coverage. And within that box, there is additional verification environment. But then the model also gets used in a virtual prototyping environment. And now that Imperas is Synopsys, we can say virtualizer is a very common, actually the most popular virtual prototyping solution in the market. I mentioned before that a lot of RISC-V projects use Imperas. Here's a partial list of our users and our processor IP partners. And then also we can see that numerous universities around the world are using Imperas, and more than 100 organizations using the free RISC-V OVP Sim Plus. And what that looks like actually is a very crowded slide with a lot of different logos on it. And then on the university and research labs slide, there's equal crowding of the logos. So, custom instructions. Let's get into that. So this is primarily what architecture exploration is in the RISC-V world. Typically, custom instructions are going to be added for RISC-V to optimize a specific application or set of applications within a domain. Thus, we get this domain-specific processor. And so the first step to this is to characterize the application to be optimized, and then add the custom instructions, evaluate, and iterate. So there we have the first box. We're going to do the simulation, use some of the tools like trace and debug and the function profiling. Now, these are instruction-accurate C models, so we do not have timing information necessarily in them. Still, what we're looking at here with optimizing for a specific application, is to look at bottlenecks in the flow, look at the number of instructions being executed. So here we can see actually what we are doing is looking at the Cha-Cha-20 encryption algorithm, and we are going to add some custom instructions for that. This is just a simple RB32IM generic core that we are running. And actually, this is running quite fast. It's running over 1 billion instructions per second. And here it is executing, hard to see from here. If I remember right, this executes about 1.3 billion instructions for this. We also run profiling tools, so function profiling to identify bottlenecks in execution. And we've got a nice report here, and we can see that this process line function, actually 21.35% of the execution time was spent in this one function. And so we'd like to reduce that bottleneck. So now we're going to develop the new custom instructions, add them to the application, add them to the model, and simulate again. So we go and do this. We can see in this first bit here that we've added to the model. You can see the new decode steps there. Let's see, this is the new decode in the model there. And then we can see some additional trace information here, and then the simulation results. So we've actually reduced the instruction count to about 670 million instructions from 1.3 billion. So a significant reduction in actual instructions. And in fact, the actual simulation speed has increased here. Even though there is no timing information in here, this is an indication that we have made the processor more efficient. And now if we look at function profiling, we can see that the process line function was reduced from 21.35% to 14.71% of the execution time. So we've significantly impacted the bottleneck. So now we can continue this approach and iterate on the custom instructions. Once we are happy with that, we can optimize and document the model, do more testing on the model, instruction coverage, line coverage, generating model documentation, and then deploy the model for all the different use cases with all the different tools. So that custom instruction flow is the heart of architecture exploration in the RISC-V world. Now let's look at processor verification. So at Imperas, we have developed not just the models, but we have also developed a full verification environment and methodology. So the first thing we think of with verification of a processor is that we are going to take a test suite, run that test suite through the RTL, run the test suite through the reference model, and compare the trace. This works very well for basic instructions, but what happens when there is an interrupt? What happens when there is some sort of outside or asynchronous event? So we have been working with our customers, collaborating with customers and partners. In Japan, NSI Techs has been a very good partner with us and helped us to develop this methodology, this lockstep continuous compare methodology. And this enables, in this environment, to verify these asynchronous events using a proprietary, patent-pending synchronization technology. So what we are going to do now is run the tests in lockstep through the RTL and the reference model and do a continuous compare of the results. So this environment, this Imperas DV, performs the scoreboarding and checking, and of course requires an RTL simulator And in spite of us being now part of Synopsys, actually, this works with VCS and Excellium from Cadence, Questa, from Siemens EDA, open source Verilator. We work with all of these. So why Imperas DV? So because Imperas is providing this environment out of the box, it provides a significant schedule reduction for the processor verification task. This can be on the order of 6 months reduction in actual schedule. It supports verification best practices, including functional coverage and constrained random test generation. The comprehensive environment supports verification of complex features, including interrupts, debug mode, privilege mode, virtual memory, multi-heart, and multi-issue and out-of-order pipelines. It supports DV of the custom features, and of course, as we've been talking about, RISC-V likes to have custom features. And customers can use the same reference model for DV and software development. And doing this provides a significant benefit on the software side, because when you get silicon back, now your software is going to come up much quicker. Our customers have typically been running software on their first silicon in a matter of days. Also, there are no other commercial solutions for RISC-V processor verification. So just to give a little bit more of a look at what this is, the same program is executed in parallel on the RTL and on the Imperas FPM fast processor model. As each instruction retires, the internal state of the RTL and the reference model is compared, and mismatches in state are reported as errors immediately, so you can exit out of the simulation. You don't have to run through the full simulation to do a trace compare at the very end. If your simulation is reporting mismatch, then let's exit out and start the debug process. So we can also see here not just the reference model and the Imperas DV environment in the test bench, but also functional coverage. So Imperas RISC-V ISACOV is system Verilog functional coverage. It is functional coverage for each extension that is part of the RISC-V ISA. It is automatically generated based on the Imperas model. Also, this is modular, so users can select only the extensions that have been implemented. It is provided as open source, so it's architected to be extendable by the user, again, for those custom instructions, but also to add things like cross coverage. It is delivered as source, and it includes documentation for use in verification plans. So not only are we integrating with System Verilog tools by providing System Verilog functional coverage, but we can provide a CSV or a Markdown file for the verification planning. So creating this code by hand would be tedious and error prone, because we are talking about 100, 200, even 300,000 lines of System Verilog to create your functional coverage. And because this is defined by the specification, it is common to all the RISC-V processors. So this is something that a vendor like Synopsys, Imperas can build. Functional coverage, of course, is a well-established DV practice, a well-established metric. And this is easy for Imperas DV customers to use, because if we go back to this flow diagram here, actually the information in that tracer coming from the RTL to the reference model is also prepared for functional coverage. So there's no additional data manipulation that is needed to get the functional coverage data. If you've set up to do verification with Imperas DV, then the functional coverage comes easily. As I mentioned, we auto-generate documentation in Markdown and CSV formats. for verification plans. And as you can see, it's just system Verilog functional coverage. And whether it's Verde or one of the other system Verilog simulation tools, the functional coverage information can, the results can just be displayed in that tool. Last, let's talk about software development. So virtual prototypes have flexibility with the Imperas FPM TLM models. So Synopsys Virtualizer for early system level verification is the tool. These virtual prototypes enable the shift left of software development. These are also high performance. The Imperas FPM itself is going to be running at hundreds of millions of instructions per second, and the rest of the System C environment and virtualizer might be running a little bit slower than that, but still you are going to have near real-time performance, with the virtual prototype. So the advantage here is that you're running very fast, and also you're able, because you're using a C model that you've built, you don't have to have the RTL. You can start the software development much earlier. Actually, for one of our leading customers building a significant AI accelerator SoC, they started software development on the virtual platform 1.5 years before tape out, and then when they got silicon back, because they had been working with the same reference model, because they had been doing all this development on the virtual prototype, software came up on an SoC with over 140 different RISC-V cores in just days. Also, the virtual prototype provides a comprehensive software environment, which is important for AI, for automotive, for other industries where software optimization and certification are required. So with just a quick word on AI, AI seems like this great use case, and there are lots of AI algorithms out there. There are lots of different architectures as well. And if you are trying to implement AI algorithms, trying to execute those on some sort of architecture, you actually need to go through a fair bit to optimize your AI compiler to run on the underlying hardware. And this is a significant use case for Imperas users. The virtual prototype is going to run at hundreds of millions of instructions per second, but it is just a C model. It is not the RTL. With Synopsys, we also have emulation and prototyping tools for RISC-V software development. These are going to use the RTL, so they're going to be actually a little bit later in the project than the virtual prototype, and run a little bit slower, but it is RTL, and that has significant advantages. So the HAPS prototyping solution is an FPGA-based prototyping solution, and ZeBu for emulation is a hardware emulator. And these can be used for hardware-software co-verification, but also for hardware-assisted verification. Because on the hardware verification side, the processor verification side, sometimes you are going to be running some very long tests. You're going to have, for example, if you wanted to boot Linux and look at the RTL response there, you would have to go through about 1 billion instructions, and doing that on an RTL simulator is just not practical. And so these tools can be used for hardware-assisted verification as well as for the software development tasks. So let's summarize here. Starting with RISC-V, RISC-V adoption is accelerating. because of the freedom of the RISC-V instruction set architecture. The high-performance instruction-accurate models are required for critical tasks. This is more than just an instruction set simulator. It really is a full-featured model. The keys to RISC-V success include architecture exploration, processor verification, software development, and these models, together with the other tools, help to accelerate these key tasks. And Synopsys, with the Imperas fast processor model, RISC-V processor models, and the Synopsys tools, have the solutions for RISC-V success. Thank you very much.
So the session is now open for the questions and discussions. So please raise your hand when you have questions. どうぞ質問ある方、お気軽に手を挙げてくださいませ。ないですか？じゃあ。
If no questions now, Synopsys has a desk out in the exhibits, and I would be happy to talk to people out there.
Okay.
Thank you.
So I have one question. So just confirmation. So your ISA model simulation speed is roughly, you said 100 MIPS, right?
Yeah. The simulation speed of the processor model is actually well over 100 MIPS. The processor model, with contrived benchmarks, the processor model actually runs about 5 billion instructions per second. But for normal software load, like booting Linux or something similar, about 500 million instructions per second. Or you can think of this as being able to boot Linux in the simulation model in just over 5 seconds.
No, it's quite fast. Yeah.
It is quite fast.
Yes.
Yes.
ご質問ございませんか？なければ、let me ask one more question, just curiosity. So when I'm a chip designer and want to implement new custom instructions, so I think, of course, your simulator system is very capable to implement custom instructions. So I have no question about that. So, but I wanted to use such new custom instruction. So the user need some compiler or some assembler, right? So at least assembler, of course. So would you recommend some methodology for that?
Sure. So, of course, when you are testing software, you want to actually have your compiler be able to compile directly for the target. This is what the Imperas model will do. They will take the RISC-V instructions and actually with the simulator translate those to x86. But what happens when you add a custom instruction? Typically, what we have seen is that the number of custom instructions is not that many. And so initially, for the architecture exploration phase of the project, our users will hand code the assembler, and then later in the project, once they have finalized the custom instructions, they will add these to the compiler.
Okay. Thank you. その他にご質問ございませんか？はい。では、so let's close this presentation.
Thank you.
Thank you very much.
Thank you.